Hello everyone, welcome to Neso Academy. We are learning theory of computation and till now we have understood finite automata that accept or reject the input strings. But have you ever thought a machine can do something more than just saying accepted or rejected? What if a machine could also produce output for every input it receives? And that's what we are going to study in this lecture. That is, finite automata with output. So the topic for this lecture is Introduction to Finite Automata with Output. But before directly going into finite automata with output, let's first take a quick recap. I have explained you that finite automata or finite state machines are broadly classified into two categories: acceptor, which are also called as finite automata without output, and transducers, which are also called as finite automata with output. Now, finite automata without output are further classified into DFA, NFA, and epsilon NFA. And in the previous lectures, we have already studied DFA, NFA, and epsilon NFA. From this lecture onwards, we are going to understand transducers or finite automata with output. They are further classified into Moore machines and Mealy machines, which we will understand in our upcoming lectures. So let's get started. A finite automaton with output is a finite state machine that not only changes states based on the input but also generates an output. What does that mean? It simply means that a finite automaton with output is a type of finite state machine, or we can say it is a type of finite automata that not only changes states based on input. That means, like a regular DFA and NFA, in finite automaton with output also, it is able to change its state from one state to another state based on an input symbol. Like in these two diagrams, you can see there is a transition from the state Q0 to the state Q1 on getting the input symbol B. Then what is the speciality in such automata? Here it is written, it also generates an output. In these two diagrams, you can see there is a transition from Q0 to Q1 on input symbol B, which we have already seen. And it is same as DFA or NFA. But there are some new elements also, like these ones and zeros. A and B are the input symbols, and 0 and 1 are the output symbols. When there is a transition from Q0 to Q1 on input symbol B, it also generates an output symbol which is 1. That's what we mean by it also generates an output. In this diagram also, if you see, when there is a transition from the state Q0 to the state Q1 on getting input symbol B, then we are having the output that is 1. So it is also generating the output symbols along with the change of states. That means it changes its state based on the input and also generates an output. That is what finite automaton with output is. Their primary purpose is not acceptance or rejection of strings. Hence, the concept of accepting or final states is not required. In these two diagrams, you can see that there is no final state, or you can say there is no accepting states. Why? Because the primary purpose of finite automaton with output is not acceptance or rejection of strings. That was the primary purpose of finite automaton without output. That was DFA, NFA, epsilon NFA. But here, the primary purpose is to generate output. That is why final states are not required in such type of automaton. They are known as transducers or output generators, as these machines generate output for the given input sequence. So whenever we give any input sequence to such automata, they will produce a corresponding output sequence. That is why they are called as transducers or output generators, because they are able to transduce or translate the given input sequence into output sequence. The two types of finite automaton with output are Mealy machines and Moore machines. These two machines we will understand in our upcoming lectures. Mealy machines are named after George H. Mealy and Moore machines are named after Edward F. Moore. Both of them were great computer scientists and mathematicians. I hope a basic introduction of finite automaton with output is clear to you. Now let's proceed with the six-tuple representation of finite automata with output. So the six-tuple representation of finite automata with output is M is equal to Q, sigma, capital delta, small delta, lambda, Q naught. So these are the six elements that are used to entirely represent a finite automaton with output. If you remember, in case of finite automata without output, DFA, NFA, epsilon NFA, we were having only 5 elements. That is why they are called as 5-tuple. But here we have 6-tuple representation because we are having a tuple containing 6 elements. Now let's understand each of these elements one by one. Q is equal to finite and non-empty set of states, which you already know. That Q is called as the finite and non-empty set of states that we have in our transition diagram. So whatever the states we are having in our transition diagram, like Q0, Q1, Q2, Q3 and so on, if we create a set of all those states, then that set is called as Q. Next one is sigma, which is input alphabet, which is set of input symbols. So whatever the input symbols we are having in our transition diagram that are responsible for the changing of states from one state to another state, those are called as input symbols, and set of such input symbols is called as input alphabet. Then we have capital delta, which is called as output alphabet, which is the set of output symbols. Like input alphabet is the set of input symbols, output alphabet is the set of output symbols. This is something new because in finite automata with output, we should have an output symbol also. And the set of such output symbols is called as output alphabet. Whatever the output we get, whenever there is a transition from one state to another state, that particular output is called as output symbol. And output symbols form the output sequence corresponding to the given input sequence. Next we have small delta, which is called as transition function. This I have explained you multiple times. Transition function of finite automata with output is exactly same as the transition function of a deterministic finite automata, that is DFA. Q cross sigma gives us Q, which means we have the current state, we have an input symbol, and we get the corresponding next state. Next we have lambda, which is called as output function. It determines the output. Like transition function determines the next state, similarly, output function determines the output that we will get. And it also tells us on what factors output depends on. Like transition function tells us that our next state depends on the current state and the current input symbol. Similarly, output function tells us on what factors our output depends on. An output function is different for Mealy machine and Moore machine. That means both the machines have different output functions, which we will understand when we will talk about Mealy machine and Moore machines in our upcoming lectures. Now the last element is Q0, which is called as initial state. So the initial state that we will have in our transition diagram is represented by Q0. So these are the 6 elements, and this was the 6-tuple representation of finite automata with output. In this way, we are done with our topic, that is Introduction to Finite Automata with Output. In the next lecture, we will begin with Mealy machines. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.